These are the top 11 new discoveries in quantum computing. Number 11. AWS launches its first proprietary quantum chip. Most people think of Amazon as the company that delivers packages and runs half the world's servers, but in 2025, they quietly took a step that puts them in the same conversation as IBM and Google. AWS introduced a superconducting quantum chip called Ocelot. For years, Amazon's quantum platform, Bracket, let scientists run experiments on hardware made by other companies, like IonQ, Rigetti, and Qwera. Now they have their own processor sitting inside their labs. It's still early. Nobody's claiming it breaks speed records or hits huge qubit counts. What matters is that a major cloud provider is building hardware instead of just renting it. When companies like Amazon invest in physical quantum chips, it usually means real-world demand is there. Banks, biotech firms, and research labs are already using AWS for encryption tests and molecular simulations. Ocelot makes quantum feel less like a lab experiment and more like a normal cloud service that people can access remotely. Number 10. Practical quantum algorithms using circuit knitting. Quantum chips today are powerful, but they're not huge. Most processors only have around 50 to 100 qubits, which is not enough for the extremely large circuits used in advanced chemistry or optimization problems. Instead of waiting for 1,000-qubit machines, researchers started using something called circuit knitting. It sounds technical, but the idea is simple. You take one big quantum problem, cut it into smaller pieces, run those pieces on multiple chips, and then let classical computers stitch the results together. In 2025, this stopped being theory and turned into real tools. Platforms like Qiskit, Cirq, and AWS Bracket now support it. Early demonstrations showed that molecular energy calculators that used to be too big for a single chip can run across multiple devices. It's slower than running everything on one large processor, but it works. It helps researchers test real quantum algorithms today, rather than waiting years for larger processors to arrive. Number 9. Google's Willow stress tested to new stability thresholds. Quantum chips are extremely sensitive. They only work inside refrigerators colder than outer space. A tiny vibration or temperature change can break the entire computation. In 2025, Google pushed its 105-qubit Willow processor through long, repeated stress tests to see if it could stay stable. The chip held coherence through extended sequences of operations and thousands of experiment cycles. This is important because early quantum processors often lost accuracy when tasks got complicated. With Willow, researchers ran quantum simulations for physics experiments and tested quantum machine learning models without the chip falling apart mid-run. Stability is a quiet milestone. It's not as flashy as quantum advantage, but it's necessary. If a processor can't survive heavy workloads, nobody can scale it. Willow's test results showed that superconducting qubits can handle real, repeated work, which is a step toward more reliable hardware. Number 8. IBM's Quantum System 2, the first modular quantum data center. Most quantum computers today look like individual lab machines. IBM took a different path and built something closer to a data center. Quantum System 2 is a full modular setup with multiple cryogenic refrigerators, racks for quantum chips, fast classical control servers, and networking built into one platform. The idea is that quantum computing will grow the same way classical supercomputers did, by connecting many processors, rather than relying on a single giant chip. In late 2024 and early 2025, IBM began linking Heron processors inside the system, letting chips share control electronics and runtime software. It's not a giant quantum supercomputer yet, but the design looks like a real facility instead of a lab demo. The system is meant to scale over time, adding more hardware modules as chips improve. It's one of the first attempts to turn quantum hardware into something that operates like an actual computing cluster, not a single experimental device. Number 7. IBM's Heron processor crushes crosstalk issues. Noise is the biggest enemy of quantum hardware. Even when a chip has enough qubits, they often interfere with each other. IBM's Heron processor was built to solve exactly that. It has 133 superconducting qubits, and the key feature is something called tunable couplers. These couplers control which qubits talk to each other and when they stay quiet. Early testing showed Heron can deliver roughly 3 to 5 times better performance than IBM's previous processors because the signals are much cleaner. Less crosstalk means fewer errors during complex algorithms. Heron is also designed for modular systems, so multiple processors can sit inside platforms like Quantum System 2. The chip is not the largest in the world, but it focuses on accuracy and stability. Reliable qubits are just as important as more qubits. If hardware keeps the noise low, researchers can run deeper circuits and get results closer to theoretical quantum models. Number 6. Microsoft's Majorana 1 topological core. Instead of building larger chips, Microsoft is trying a different approach. Their Majorana 1 chip is based on topological qubits, which use exotic quantum states that are more stable than ordinary qubits. The idea is that these qubits are protected from certain types of noise because of the way quantum information is stored. The Majorana 1 device is a small prototype. Not a huge processor, but the architecture matters. Topological qubits have been a research goal for more than a decade. If they work, they could deliver fault tolerance without needing as much error correction. Traditional superconducting or trapped ion systems need thousands of physical qubits to create a handful of logical ones. Microsoft's approach aims to shrink the gap. Majorana 1 will not replace existing platforms overnight, but it shows a path towards stable qubits that hold their state longer, which is one of the biggest challenges in quantum computing. Number 5. Quantum molecular geometry with a nuclear spin. Molecular ruler. Quantum computers are not just about speed. Some problems are simply out of reach for classical machines. In 2025, researchers demonstrated a new technique using quantum many-body nuclear spin echoes as a kind of molecular ruler. The idea is to measure the geometry of molecules with extremely high precision. Classical methods, including spectroscopy and electron microscopy, can struggle with certain structures because the signals overlap or the sample's too small. Quantum spin echoes can probe interactions inside a molecule in a way classical sensors cannot. This does not mean quantum computers replace chemistry labs, but it expands what scientists can measure. Better molecular geometry data could help with drug discovery, materials research, and chemical engineering. It's a quiet breakthrough, but it shows that quantum technology is not limited to computing tasks. It can act as a scientific instrument that reveals information the classical world cannot capture. Number 4. D-Wave simulates false vacuum decay. Quantum computing is not just about breaking encryption or speeding up chemistry. Some experiments deal with the structure of the universe itself. In 2025, researchers using D-Wave's quantum annealer simulated a process called false vacuum decay. It's a theoretical event in physics where a stable region of space could suddenly jump to a lower energy state. Classical computers struggle with this because the calculations scale too quickly and require enormous memory. D-Wave system modeled the energy landscape in a way classical systems cannot reproduce at scale. It's still a scientific demonstration, not a prediction of cosmic events, but it shows how quantum devices can explore areas of physics that were mostly theoretical before. Even though annealers work differently from gate-based quantum computers, this experiment highlights that different quantum technologies may specialize in different scientific problems. Number 3. IBM's Condor breaks the 1,000-qubit barrier. For years, quantum processors grew slowly, from single digits to a few dozen qubits. In 2025, IBM crossed a symbolic milestone with Condor, a superconducting chip containing 1,121 qubits. It's the largest publicly reported quantum processor to date. This does not automatically mean it can outperform classical supercomputers, but it represents a major leap in engineering. The challenge is not only adding qubits, but keeping them connected and stable without excessive noise. Condor also fits into IBM's modular roadmap, which means multiple chips may eventually work together inside systems like Quantum System 2. It proves that large-scale superconducting architecture is possible in real hardware, not just on research slides. Classical computers took decades to scale from tiny prototypes to the massive systems we have now. Condor feels like that early stage, where hardware finally starts looking big enough for complex workloads in the future. Number 2, certified true randomness from a 56-qubit quantum computer. There is normal randomness, like rolling dice, and then there is certified randomness. In 2025, a 56-qubit quantum processor generated randomness that could be mathematically verified as unpredictable. That matters because cryptography depends on random numbers. If randomness can be predicted, encryption can be broken. Classical computers generate pseudo-random numbers, which follow patterns if someone knows the algorithm. Quantum randomness comes from the behavior of quantum states, which are fundamentally unpredictable. The breakthrough is that researchers can now prove the randomness is real using mathematical certifications. Banks, secure messaging platforms, and government agencies have already shown interest in this kind of technology because it could form the basis of long-term data protection in a world where classical security might fail. It's a small experiment with huge consequences. Number 1. Google proves real quantum advantage in hardware. For years, quantum advantage was a theoretical goal. Companies published papers claiming breakthroughs, but the real question was whether a quantum computer could solve a practical problem faster than the best classical supercomputers on Earth. In 2025, Google demonstrated that using an algorithm called quantum echoes, running on the Willow processor. The hardware solved a physics-grade problem more than 13,000 times faster than classical simulations. Unlike earlier milestones, this was not just a random circuit sampling test. It was a structured algorithm applied to real scientific modeling. The key point is that it ran on an actual processor, not a simulated environment. It does not mean quantum computers replace classical machines, but it shows that certain scientific tasks have now crossed the line where classical systems are no longer competitive. It's one of the clearest demonstrations of practical quantum speedup to date. If you made it this far, let us know what you think in the comment section below. For more interesting topics, make sure you check out the recommended video that you see on the screen right now. Thanks for watching.